Первый слайд. Так. Что-то резко. А, вот теперь резко, да. Да. Ага, вот теперь понятно. Так, можно начинать. Пожалуйста. Сосузгаш.
Добрый день, уважаемые участники семинара. Если разрешите, я буду продолжать на английском языке.
Пожалуйста.
Today's talk is devoted to the certain properties of Bivariate Mittag-Leffler function E2, and we show some application of this function in considering direct and inverse problems for PDEs involving the Prabhakar fractional derivative. So the first, I will stop shortly about the multivariable Mittag-Leffler type functions, and then I will concentrate my attention to the E2 Bivariate Mittag-Leffler function, showing the integral representation, some estimates, and further some lower and upper bounds for this function. And then I will talk about some ongoing investigations. So let me start with the first multivariable Mittag-Leffler function. It was introduced in 1997 by Gorenflo and Luchko. So it has the following form. And for this function, different authors studied recurrence formulas, differentiation and integration formulas, some asymptotics. I will talk in detail about this function in two variable case because it will be just a particular case of our bivariate function E2. Then later in 2021, Bajlekov and Bajlekova generalized this multivariable Mittag-Leffler type function in terms of Prabhakar. So they included this additional parameter delta. So if delta is equal to 0, we will get the Gorenflo-Luchko function. And for this function, they also studied some recurrence relations, integration and differentiation formulas, and also additionally complete monotonicity as well, including this asymptotics. So this function also nowadays becomes popular. And more general multivariable Mittag-Leffler function was introduced in 2011 by Saxena and Kalla. It has the following form. So you can see that here the Pochhamber symbol, which can be written by the ratio of two gamma functions. Several this kind of Pochhamber symbols appear here. And for this function also the certain properties was studied. And also they considered some integral operators with this kernel. And the first attention to this multivariable, in particular two variable Mittag-Leffler type function, was after publication of this work, 2013. So in this work, the authors introduced this function E1, they call it E1, and they studied the region of convergence and also the system of hypergeometric equations which satisfy this bivariate Mittag-Leffler type function E1. And also they found some Euler type integral representation, Laplace integral transforms, and etc. So our interest for this function was connected with the following properties. So the regular two-parameter Mittag-Leffler function can be represented by this bivariate Mittag-Leffler function. In fact, you can see that the second variable also the same as the first. So we represent this two-parameter Mittag-Leffler function via this bivariate E1. So the solution for the inverse source non-local problem for mixed type equation with the Caputo fractional differential operator was represented by this function. And for this function, we have studied certain properties, in particular the estimate for this function.
Sorry, can you zoom to make it this index is a little bit bigger? Because it's the indexes are too small.
Oh, really?
You cannot.
Oh.
No zoom, yeah?
So it is a full screen, but I can try.
Okay. Please.
I can try to make this kind of zoom.
No. Doesn't matter. Oh, yeah. That's good.
So,
okay, thank you.
Yeah. So, I'm sorry. I will continue by this way.
Yeah.
Then, at the same work, they introduced the function what we are today will consider. They just introduced this function and did not study it. They said that this function also can be studied by similar way. Later on, I contacted the authors whether they studied or not, and they told me that they did not study. So that function was kind of okay. So it's more general than E1, but still was not interesting for us. But later on, when we started to work with the Prabhakar fractional derivative, we found that this is the subdiffusion equation, the Cauchy problem, and this is the Prabhakar derivative. And the solution was represented by the infinite series of Prabhakar function. The Prabhakar function is just a generalized function of Mittag-Leffler. Sometimes they call a three-parameter Mittag-Leffler function. So for us, it was interesting. Can we write down this form via the bivariate Mittag-Leffler function? First, we started to rewrite it with E1, but we failed. Then we consider E2. So then we could be able to consider it, to rewrite it with E2. So with Professor Hassanov, we considered this kind of subdiffusion equation with a regularized Prabhakar fractional derivative. And we found the solution in this infinite series form, representing the solution with the E2 function. And in this case, to prove the uniform convergence of this infinite series, we need to estimate E2. And for this aim, we found the integral representation, but with certain restriction on parameters. So alpha 3 equal to alpha 1 and beta 2 equal to beta 1. But in fact, as you see here in the solution, we have already the particular case of E2. So here, because of this restriction, our parameter gamma, which is the part of the parameters of Prabhakar fractional derivative, should be equal to beta. And also the parameter alpha should be equal to 1. So by this restriction, we represented our solution by this noun product of noun special functions, including the two-parameter Mittag-Leffler function. But for our case, it is just a two-parameter Mittag-Leffler function and an exponential function with the second variable. So for this case, since the estimation of E beta beta is already known, and then we could be able to get the estimation for E2 as well. So then, of course, here in our case, we have the lambda, which is kp square minus kp square. And delta is just a parameter of the Prabhakar fractional derivative. So we can assume that delta not positive. So by this way, we can estimate our bivariate function by some constant. Here, we could not get the similar estimate as in the case of two-parameter Mittag-Leffler function because of this integral. So in any case, we could be able to approximate the estimate by constant, which was enough for us to get the proof of uniform convergence of infinite series. Then, okay, so we stopped with this and we were satisfied with the result. Then, with Professor Hassan, we were interested, can we introduce the other Bivariate Mittag-Leffler functions? So the first motivation comes to just generalize hypergeometric functions. And we choose the Horn hypergeometric functions. And then we just replace, for example, here, the lower index is m plus n. So we multiplied with the parameters alpha 1 and beta 1, so that they can be non-integers. So by this way, we generalized these hypergeometric functions into the Mittag-Leffler type functions. So several this kind of functions were introduced, and we studied standard package of properties like integral representation, some recurrence relation, and etc. But this was kind of the properties of these bivariate functions, which are not linked with the certain PDEs or the solutions, and etc. So then, okay, so I will continue later on, but now I would like to mention some noun bivariate Mittag-Leffler type function. Recently, so we found the information, but it was published in 2022, but we found it a bit later. The Tarasov also, when he considered the Cauchy problem for the differential equation involving the Prabhakar fractional derivative, he also got the solution with the infinite series of the Prabhakar function. He used a Laplace transform, but he introduced this kind of bivariate Mittag-Leffler function and then wrote the solution in terms of this. Actually, when we call the bivariate, but when we apply, we always use the same variable, so it can be kind of counted as a single variable, but with the double series. So actually, he just introduced it, but did not study any properties. He just rewrite the solution in this form. Then we found other bivariate Mittag-Leffler type functions. For example, the works by Ozarslan and Fernandez, etc. They introduced this kind of bivariate functions, which are just will be particular case of our function, but they attacked this function in other point of view, some fractional calculus point of view, some
Is it possible to construct? Is it possible to construct green function? Is the fundamental solution of this fractional?
Yes. Yeah, and nowadays we trying to consider almost done. We constructed the green function for the certain boundary problems, and nowadays it's ongoing results. So we have almost done results on this.
Some fractional differential equation.
Yes.
For some fractional differential.
For example, subdiffusion equation with the Prabhakar fractional derivative. So we can consider first or second initial boundary problem. And as it was done in a Caputo-Riemann-Liouville case by Professor Pschou, so he constructed the green functions, which was written by right-type functions. So in a similar way, we can construct the green function, but in that green function, the bivariate Mittag-Leffler functions will be participated. So it is almost done. So, but these authors, they introduced even the fractional integral operators, kind of two-dimensional. So in both direction, x and y. So they introduced the integral operators, and they studied some certain properties. And also because of this motivation, they just separated into the families of bivariate Mittag-Leffler functions, as you see here. And based on this function, they introduced the integral operators. For them, it was interesting to have whether these integral operators have semigroup properties. And that was kind of for them the motivation. And they introduced the trivariate and etc. And the sum of functions they found in the solution of some system of differential equations, etc. So, but this is not my main target. That's why I don't want to stop on them. Now let's come back to the E2. So this Bivariate Mittag-Leffler function was first time used by us just representing this infinite series of Prabhakar function. We have this E2 and we just use it ready solution. But we wanted to make sure that can we get the same solution by the other method. So before us, it was done by Mikuchinsky operational method and the Laplace transform. And but we now in this work we equivalently reduced this corresponding Cauchy problem to the Volterra integral equation, and we solved it by successive iteration method. And then we got the same solution. And then we started to consider some mixed equation. And for mixed equation, the previous integral representation was not good because there was a restriction that the gamma should be equal to beta. Beta is kind of linked with the fractional derivative. So in subdiffusion case, it is between 0 and 1. And for the fractional wave, it will be between 1 and 2. When you consider both equation in once, so it's a wave diffusion process, in that case, that integral representation will not be good because the gamma is just the same gamma. So you cannot assume that it should be equal to fractional orders between 0 and 1 and 1 and 2 at once. So that's why we try to find another integral representation. And with this also with this restriction, but this restriction is was acceptable for us. And we represented this E2 by the product of two right type functions. So right type function, and this representation was good enough for us because we have already ready results about the estimation of these functions by Professor Pschu. And then we have used these results and we got the estimate for E2. And the estimate is the following. And also we can estimate it not just by constant, by some arguments as well with the power theta. But unfortunately, because of the restriction of related to the other parameters of this function, we had to assume that between theta should be between 0 and half. And in the case of the right type function, the Professor Pschu, when he considered the similar estimate, the theta was between 0 and 1. But in our case, we need to restrict ourselves into this case. But when we started to use this estimate, we need to assume that theta equal to 0 just to simplify calculations. But in some works, we use the same estimation, but it doesn't help us, like in the case of Mittag-Leffler function, to reduce the regularity of the given data because the power is between 0 and half, so it's kind of almost no influence of this lambda. For example, lambda will appear here, but it doesn't help us to reduce the regularity.
X, Y are negative or?
XY is a positive.
What does it mean minus
no,
X?
XY is in our case will be negative. For this
Yes.
integral for this integral representation, it doesn't matter.
But what does it mean? Minus X in the power of theta if the theta is not integer? Because what kind of part of this complex function do you choose? If What does it mean?
In our case, x is kind of lambda k multiplied by some time in power. And y is a delta multiplied time in some time.
Theta is less than 1 or 2. It means
Yes.
that, yes, it's not integral. And what's the meaning of minus 1 in the power of theta, for example? Maybe x is near the 0. Maybe x is negative. Yeah. In this case, it would be understandable. Okay, let's continue. Yeah.
Okay.
The same about minus y.
Yeah. As I explained it, this integral representation was important for us because we consider the mixed time fractional mixed equations. So I can mention these works related with this. We considered the direct problems and then we have used this integral representation. And also this integral representation was important for us to prove this kind of statement. And when we consider mixed fractional differential equations, in denominator, we will have this kind of expression for which we assume that it is not equal to 0. And also since k is just a parameter of this infinite series, can go to infinity, we need to consider the behavior of this expression as well when k tends to infinity. And because of this integral representation, we can prove that when k goes to infinity, this expression will be equal to a. A is some positive time. So this was done just due to this integral representation. So we have this product of two right type functions. And for these right type functions, we have ready results. So Professor Pshu studied these properties. And based on this, we can use these asymptotic formulas and get at the end, we will get some fixed number. So when k goes to infinity, so denominator the behavior of denominator is clear. So it will be equal to a. And we can assume that when it's not equal to 0, we can consider some properties. And of course, when it is equal to 0, there might be some non-trivial solution of the problem. And that
It
was
means that
kind
the sum of these two integrals equals 0, yeah? If this limit...
Yeah, because of here, when we have the zeta, the argument of this...
You have the sum of two double integrals, and this sum is 0, yeah?
Yes, because of this goes to 0, and this goes to 0. Okay. Both of them, because of this, will be 0, and only the first term will remain.
Okay.
Yeah, and that was helpful for us to get this kind of result. But this integral representation did not guarantee us positivity to prove the positivity of E2. And we need that kind of property when we consider the inverse initial problem for this equation, the equation 11, where the PhD, this Hilfer-Prabhakar fractional derivative. So I will show the definition. So but the fractional order is between 0 and 1. And in this case, here the novelty was just the usage of this 14, and also the inverse initial problem was not considered before. So the inverse initial problem, so this is the Hilfer-Prabhakar derivative. So this is the Prabhakar integral, and this is just a combination. So inverse initial problem was to find the initial data imposing the overdetermination conditions. So for certain fixed time, we have the information, and we would like to recover the initial data. So in this case, when we find the initial data in denominator, we have this expression. So we need to show that it is not equal to 0. And of course, here E2 has certain particular cases of the parameters, which is linked with the Hilfer-Prabhakar derivative here, the mu between 0 and 1. And gamma is a parameter of the Prabhakar fractional derivative. Beta is a fractional order. Alpha also is a parameter. So in this case, to prove this function is a positive, we need to find another integral representation. And here we need to restrict ourselves as follows. So alpha should be equal to 1, and mu cannot be equal to 0 and 1. When mu equal to 0 or 1, we will get the Caputo or Riemann-Liouville type of Prabhakar fractional derivative. And the gamma equal to beta is also kind of condition, and which doesn't allow us to get the classical Riemann-Liouville or Caputo Prabhakar derivative, because when gamma is equal to 0, we will get. But since gamma equal to beta, and it cannot be 0, so we cannot get the classical fractional derivatives. So this integral representation is not valid for the classical case. So we will get this kind of sum of two integrals, where in the second integral we have a two-parameter Mittag-Leffler function. And since for this function, and this is just a sketch of proof, here we will use the integral of beta function. So it is a regular approach to get this kind of integral representations. So when we use the beta function, so we will eliminate this combination where we have m and j is mixed in the argument of gamma function. So in that case, we cannot we cannot express it with the noun function. For this, we use just the integral of beta function, and we get this kind of product of two series, which can be written, this is just the exponential function, and this is just a two-parameter Mittag-Leffler function. And by this way, we got this integral representation. Now we can use the properties of this function. As you see here, when gamma is actually beta between 0 and 1, we have a lower bound for this function, and the exponential function when delta is negative, so can be also restricted. I mean, we can find a lower bound. And then because of this integral representation, we can state that our function is a positive. So in denominator, we don't have a 0. So by this way, we can consider inverse initial problem. And of course, here, this is not the general case, and we're still continuing to prove this kind of positivity for more general cases, but still we did not succeed. But we can somehow generalize these results, imposing less restrictions to the parameter. I will show a bit later.
It's a greater, it's not only positive, but it's greater of some constant which is positive, yeah?
Yes.
No. Okay.
Yeah.
Because you need to estimate from the below.
Yes, yes.
Yeah, okay.
And you can see here the exact constants.
No.
And now, as I said, first, Goran-Floluchko function. And this function is important for us when we consider multi-term cases. For example, this two-variable case will appear when we consider two Caputo or two Riemann-Liouville fractional derivatives in differential equation. And in the solution, you will get this kind of this function. And for this function, I didn't see result on positivity, but in any case, maybe I didn't find. But here, this function can be represented as a particular case of E2. So we have here the particular case, but the parameters are a bit different than what we considered before. And here, we find another integral representation for this particular case. Just we were interested to consider this function, and I will show the application why we need this result. So here, our alpha between 0 and 1, alpha means this parameter, and the beta should be greater than alpha. And we can find such an epsilon, real number in the epsilon, which satisfy this double inequality, for which the following integral representation holds true. And I will show the short sketch. For this, we will write down this double series form and multiply and divide by this product of two gamma function. And we will use, as you see here, we would like to use this formula. So A plus 1 B, we have this A, it was kind of, when you sum up this A and B, you will get the denominator, what we have initially. So we just choose this expression according to this. And when we use this integral of beta function, we get another kind of ratio of gamma function. Initially, we have this gamma function, and we divide by this product of two gamma function. That is okay because it just depends on m, but this one depends on m and n. That is why we separately consider this kind of ratio. Unfortunately, we have this kind of formula. This ratio can be represented by the right function, the integral of right function. But here are the certain conditions on the parameters, nu, beta bar, and mu. So in this case, we try to use this formula for this ratio, and we choose nu as m plus n plus 1. So our m and n starts from 0, 1, 2, and then etc. So in this case, nu is positive, is fulfilled. So beta bar and mu we will choose as follows according to the expression of this argument. So here mu should be equal to b minus epsilon and alpha. So here we introduce the epsilon, yeah, and we can choose the epsilon as a beta minus alpha. So here all these conditions will be fulfilled. We will impose the conditions on beta and alpha in order to get these conditions. So then remaining gamma functions, we will use the expressions, infinite series form of expression exponential function and the right function, and then we get the desired integral representation. And that integral representation, why is important? Because we have, as I said, if we consider two Caputo derivatives in the differential equations, and we consider Cauchy problem for this, solution will be expressed here, the alpha 1 and alpha 2 between 0 and 1. I will stop when alpha 1 is between 1 and 2, which can be kind of generalization of a fractional telegraph equation. Here, okay, so alpha 1 and alpha 2 between 0 and 1. So solution can be written in this form, but we can use the properties of this Gorenflot-Luchko function in two variable case, and we rewrite the solution in this form. And for us, it's a bit important because when we consider inverse initial problem, the expression is easy to prove positiveness. This is not a kind of plus minus, so there is only the positive things will be added up. So here A, B is the initial data, and we can impose this kind of overdetermination condition for fixed time and then find A or B. Let's say B is unknown. If B is unknown, so when we find the unknown constant B, so we need to divide by this expression. So for us, it's important that it shouldn't be equal to 0 for that values. And we can use that integral representation. In our case, rho is equal to 1, alpha is equal to this difference, and beta is equal to alpha 1. And our epsilon will be in this interval. And for mu positive, because in our case, mu should be positive. Mu is just a coefficient of the differential equation, so we can impose the condition on this. So in that case, according to the integral representation, we can prove that it is positive. And also for the case of if A is unknown, we have this summation, and we need to additionally impose that lambda should be positive. And this is also not a restriction, because when we consider PDEs in terms of T, we will get the same equation, but with the, let's say, the KP square, or always the lambda is positive in our case. So that's why it's kind of not a strict restriction. So we can prove that it is positive. Why it is positive? Here, let me come back to the integral representation. Yes, here, in this integral representation, we have a product of two right functions. This is a particular case of right type function. When these parameters equal to 1, 1, we get the right functions. So right function, when this parameter is between 0 and 1, it was proved that it is a positive for negative arguments. And here, also we have a kind of beta is also between 0 and 1. And when x is negative, in our case, we have here the minus mu. So this is also positive. So this whole product is positive, and the exponential function is in terms of y, we can choose the parameter what we have. So this is also, even if here it doesn't matter that the y is a positive, negative, because it's always we have the positive result. And why it doesn't work for alpha 1, let's say between 1 and 2, the first order of the Caputo derivative. In that case, we get this kind of result here, especially here. The beta is just the first derivative, what we have in the differential equation. So if it is greater than 1, so the positivity of this function is not known. That is why we cannot apply for that case. Maybe somehow we can restrict ourselves beta as between 1 and 4/3, and then say something, but we didn't go further. Just for us, it was important to have the first result for this Gorham-Flow-Luchko function. And this result also we did not publish yet, because this is kind of...
Did you send it to archive?
This was just recently obtained. We just wanted to make sure that can we cover this Gorham-Flow-Luchko function in two variable case by our function E2, and can we prove also the positivity for that function? So actually, in fact, one can consider the somehow the maybe inverse initial problems for such problems with these two Caputo derivatives, and then using this result can be...
But both derivatives are less than 1, yeah?
Yeah, between 0 and 1. But when first derivative between 1 and 2, our integral representation cannot guarantee that it is positive because the right function has no such a property for that case.
Maybe in this case, the problem will be positive.
Yeah. And in the classical case, it is still open question. There is only the results by
What do you
Professor
mean
Pskov
classical?
that
What do you mean classical when alpha is negative?
classical means that the Caputo or Riemann-Leibel case.
Yeah, okay. It became
Classical
possible.
fractional
Yeah,
derivative.
okay.
So the next attempt was can we get the double estimate as it was done for the two-parameter Mittag-Leffler function by Simon and the co-authors. So can we get similar results for E2? And we just try to use this integral representation. Of course, here the restrictions are strong. So alpha equal to 1 and gamma equal to beta. And we got this restriction. But when we try to prove this double estimate, we have to restrict ourselves. Beta should be between 0 and 1 because this double estimate for this function exists only for this case. And also we need to put this restriction, delta minus beta should be greater than 2 because of the form of these integrals.
What does it mean in these inequalities? I1, I2, what is it?
Yeah, I will show the I1 and I2.
This integral.
Yes, here we have an exponential function. In fact, the exponential
y is positive. Y maybe it's negative, yeah?
Y is negative.
Yeah. In this case, okay, this I try to understand. It's not bad if x is 0, yeah? Not bad.
Yes.
And x, when x tends to infinity, it's close to 0 like 1 or x squared, yeah?
Yeah.
The denominator should be like x squared.
Yes. And then for these endpoints, we have in one endpoint, we have a problem. And for this, we need to suppose that delta minus beta minus 2 should be positive.
Yeah, and when x and y are 0, it's positive. It's positive too. Yeah, and it doesn't equal to 0 nowhere. Yeah, it's I1 and I2. Both,
I do the same, only the constants will be different.
C, CY, C2, yeah?
Yeah.
It looks, now it's understandable why beta is less than 1. Yeah, okay. Okay.
And the interesting case is, we are still working on this, alpha equal to 1 reduces us to get this exponential function. But when we say that alpha is greater than 1, then instead of exponential function, we will get the right type function. So this integral will be not exponential, but right type function. So
like polynomial, no?
Yeah, right type function is kind of is additional gamma function in the denominator.
It has a very good estimate, like polynomial, if alpha is different from 1. Yeah.
And we need to study
get
this convergence of this integral with certain restriction on the parameter.
Okay.
Yeah, in that case, we can assume that alpha is not equal to 1, but greater than 1. It is also important, I will mention a bit later, why alpha equal to 1 is a strong restriction for us.
Yeah, it's very interesting. This is a real classical case when alpha is equal to 1, and it's the worst case, I think. For example, for backward problem, for Cauchy problem, and so on. Yeah, because okay.
Actually, in fact, the alpha is a parameter which appears in the fractional operator, in a Caputo operator. It is kind of this alpha, beta, gamma. So if alpha equal to 1, we got in alpha equal to 1 case, we got the exponential function.
Yes,
So
yes, only.
in the kernel of the Prabhakar function, we get the exponential function.
Yeah.
This is a bit restriction, and also the gamma equal to beta, because when gamma is equal to 0, we get the classical Caputo derivative. And also we can get the Caputo derivative when y is equal to 0. So this can be applied for the, actually, in fact, we get when y equal to 0, we get this function. Not beta beta, but with a bit another form. But it coincides with the result of Simon if y equal to 0. We get the
Okay.
same result as Simon. So this is just a explanation of how we get it. But in this case, as you see here, we multiplied and divided by this function. And here, when we consider alpha equal to 1, we directly get the dependence of the argument will be only from n, and then it's easy for us to consider with this classical Mittag-Leffler function. But if it's not, let's say here, if it's not equal to 1, then we will get the right type function instead of exponential function. So, but alpha exactly it should be greater than 1, because here if it's negative, n is 0, 1, 2, so we cannot provide that b is positive in order to use the beta function. So that is why alpha greater or equal to 1. We choose the case alpha equal to 1, but we can consider alpha greater than 1, but we need to study the convergence of the integrals. So what we are doing, it is in process, but we didn't get the result yet.
We consider analytical continuation of this integral, or using integration by parts, you can assume that b can be -2. Oh, okay,
Yeah.
okay. Please
Yeah,
continue.
yeah. For this formula, yes, yes. Yeah, there is not
Okay.
such a restriction for this. Okay, so as I said, we use the Simon's results for this double estimate of this function, and we will get the result what we obtained. But this is also was not published, and I don't know, we need to apply for certain problems to publish it. As you already realized, I always state the statements as a lemma, because in my opinion, it's not a main result. So it's kind of always auxiliary results. And once we have some application, then we can use this result as an auxiliary and then write
This double estimate was proved by Simon, yeah?
Yes, this is
Okay.
proposition 4. And when beta between 0 and 1.
Yeah, okay.
And now we try to consider when beta, actually the fractional order between 1 and 2. Can we get the positivity or something in this case for E2? So then we have this kind of integral representation. Of course, here beta is between 1 and 2. This is not good for between 0 and 1. So it's specially done for that case. And here, fortunately, we have a less restriction on gamma. Gamma is not equal to 1, beta. Gamma is less than beta minus 1. So you can consider it like between 0 and 1, because beta is between 1 and 2. And delta is greater than gamma plus 1. And we can find such a ij, real numbers, such that the following two inequalities should hold. And then we can have this kind of integral representation where we have a product of two functions. One is a right function, and then another one is right type function. So in this case, so why this integral representation is important. As you see here, this expression, even beta between 1 and 2, this expression still between 0 and 1, because we have this gamma less than beta 1, so it is less than 1, and it is positive. So here we can use the positivity of right function. And here also the parameter should satisfy certain conditions to state that this right type function is also positive. I will mention later. So let me just give this sketch of the proof for this integral representation. Again, we manipulate with the gamma function. I will just multiply and divide by this gamma function. Our condition is just provide us to do this. So we have here, let me come back to the integral representation and say about this term. We have a gamma plus 1, of course, here, and also here 2, 1. I will explain why we consider this, exactly this case. And it can be done for gamma, not gamma plus 1. In that here 1, 1 also. So we just do it specially because we need it in other evaluations. So this is also the recently done, but not published, not applied yet. So we multiply and divide by this expression. And in fact, we have in a series form this and also this. And when we multiply by this function, we choose this argument because of this integral of beta function. And we need to divide it. So when we divide, we have no problem with this because it depends only from m. And again, we multiply and divide by this expression. We just imposing I and j is just we choose this special form minus j, but it can be just a plus j, and j can be chosen by another way, positive, negative. But here the I and j are just real numbers. So we assume this and multiply and divide by this expression. And for this ratio, we again use this formula. And in order to provide the fulfillment of these conditions, we need to impose the certain conditions on what we have, I, j, beta, delta, and the gamma. So all these conditions were imposed to provide these conditions, and we could be able to use this formula. And then remaining parts, what we have in the infinite series, this is equivalent to this function, and this is the right function. So by this way, we get that integral representation. And why that integral representation is important, as I already mentioned, that we can prove the positivity of this function. And as you see here, we have the result of Professor Psou, where these conditions is fulfilled. Then for x positive means that argument is negative. That right type function, this is not a capital A, it should be small l, e. So it's a right type function as a positive. Of course, here for beta bar, there is a condition should be between 0 and 1. So in our case, these two functions just coincide to this case, and we can claim that they are positive. And because of this integral representation, we have the positivity of E2. Okay, so if we have this positivity E2, then now we can somehow apply for the inverse initial problems and etc. But for us, it was interesting to consider that expression delta k, what was appeared in when we consider mixed equations. And in order to use that result to that case, we have to consider this kind of recurrence relation, which was not available, and we have to prove it. So this, when you multiply by the first argument, and you can rewrite it in this case, in this form. So this is a classical two-parameter Mittag-Leffler function. So if you rewrite this expression in this form, so it can be useful for us. So I will skip the proof, move to this case. The proof is almost similar as before, but here we need to just separate the n equal to 0 case. So we have this series, which gives us a Mittag-Leffler function of two parameters, and then n equal to 1, we just replace again in order to rewrite it as E2. So we have here product of two arguments. So then we use the recurrence formula, this for two-parameter Mittag-Leffler function. And then this delta k, which was written in this form, instead of capital T was A before. So it's just a fixed time. So we rewrite in this form. Now you can see here, first argument multiplied to E2. So we can use that recurrence relation to get the more suitable form for us. When we use that recurrence relation, we got 1 over gamma 2, which is equal to 1 and can be cancelled with this. So at the end, we got this form. So here we have minus, but delta, if it's negative, so we can have this positive item here. And since we can prove that these are positive, only the part which might be negative is this. And now we know that this function, when beta is between 1 and 4 over 3, it has no real zeros. But this function has certain zeros. But now we need to consider the summation of these two functions. But what I find is for small arguments, it is positive. But for greater arguments, it might be negative as well. So here, when k goes to infinity, so we may have a negative part. So delta k still might be equal to 0. And in this case, it's more clear that we have these classical Mittag-Leffler functions, and also here when beta is between 1 and 2, this expressions has a countable number of zeros. So then it gives us more belief that delta k is equal to 0 only in a finite time, for finite k's. Okay, so let us check whether these cases are good for our integral representation. Can we find such a I and j? In the first case, delta is equal to beta plus 2. So this case, our case is alpha equal to 1. So beta plus 2. Other parameters will just coincide. So in this case, I can choose I as 1 and j equal to 4. So all these conditions of the lemma will be fulfilled because we have here 3 minus beta, beta plus 2 less than 4. So when beta is between 1 and 2, so this double estimate holds. And for the next case, when delta equal to beta plus 3, we can choose another ij. So this double inequality holds, and still we can state that function E2 is a positive. So when beta is between 1 and 2, still that function is a positive. In the classical case, when E2 coincides with the Mittag-Leffler function, we cannot claim that positivity. But in that case, E2 case, we can claim. But what is the problem? Why we cannot, why this is a contradiction we have? Because in that case, we cannot get from E2 the classical Mittag-Leffler function because our gamma cannot be 0. Cannot be 0, and we cannot get the Caputo derivative, and as a consequence, as in the solution, we cannot get the Mittag-Leffler function. So, and also what I mentioned about the alpha, when alpha is equal to 1, the regularized Prabhakar derivative will have in the kernel not the Prabhakar function, but the exponential function. This is kind of a bit strong restriction because it's already not a Prabhakar fractional derivative. It's just a particular case. But now we are working on this direction, and many things should be improved. So we expect some results on this direction. So now at the end, I would like to mention my co-authors, which these results were obtained by the contribution of my co-authors. So thank you very much for your attention.
Thank you very much. Sorry, that was interesting. Are there any questions? Есть ли какие-то вопросы, может быть?
Можно
Да, пожалуйста.
или даже комментарий?
Можно
Вопрос,
на русском.
комментарий. Можно по-русски,
Да.
да? Или
Конечно,
Да.
конечно, да.
Там вот где формула 21, по-моему, там было, вот перед этим, перед формулой 21. Ну, где
Так.
доказательства,
Сейчас
проводили схему доказательства, и там вот здесь можно остановиться даже. Вот здесь тоже, вот предыдущий. Следующий слайд. Следующий.
Вот это, да?
Нет, следующий слайд. Вот эта формула, где с функцией Райта, этот несобственный интеграл. Эта формула остается верна, если для бета любого знака. Не обязательно бета быть положительной. Поэтому...
То есть это требование не обязательное, значит.
То есть интеграл будет сходиться, и результат будет такой же, если бета любого знака. Для любого вещественного. Даже если бета нулю, или там минус единицы, минус двойки, то и ню может быть...
Да. Тогда...
Чуть-чуть отрицательным быть, там больше минус единицы.
Речь идет именно об этом интеграле, потому что в других формулах бета должно быть положительным, конечно.
Ну, я так понял, что вот здесь вы как бы старались его сделать положительным. То есть, поэтому...
Да.
Вот. И вот теперь к формуле 21, если можно.
Yes. Я извиняюсь, сейчас работает очень медленно.
Уже вот мы приблизились.
Так, 21. Вот это?
Да, вот такие задачи для таких уравнений. Ну, то есть, и когда много производных, есть решения, которые выражаются в терминах там свертки, гиперсвертки с функцией Райта. Вот есть Луиза Гадзева, вот у нее работ много, то есть она краевые задачи решает там, для таких уровней, именно с капудопроизводными, там вот здесь стоит сумма. И если вы сравните ее решение вот с вашим решением, возможно, вы сможете получить какие-то вот новые представления для ваших вот этих многопараметрических функций. То есть
это уравнение можно рассматривать как некое обобщение телеграфного уравнения, нет?
Если альфа-1 между единицей и 2.
Да, но в принципе у телеграфного уравнения там первый порядок и второй. Альфа-1 равно двойке, альфа-2 равно единице. Или наоборот, да.
Это же обыкновенное
здесь у вас дробное, да.
Нет, это же обыкновенное уравнение, то есть здесь только по t производной.
Ну да, по t.
Ну там, да, если рассмотреть уравнение частным производным, по x добавить что-то.
Если справа поставить по x, а что такое? Ну, понятно.
Если вы сравните свои решения с ее решениями, то вот для ваших функций, вот этих многопараметрических, возможно, какие-то другие представления вы получите.
Да.
Потому что у него есть эти решения, но в другом виде.
Да. Спасибо за информацию.
Спасибо за интересно.
Есть еще предложения или замечания? Рашам Амжарович, создаем? У вас
все нормально, да. По-моему, вот это 21, Арсений Владимирович, у вас же тоже есть, по-моему, такие уравнения, вы рассматривали?
Ну, они с Римана, да, там Римана Лювиля есть, да.
Ну да, там можно...
Они друг друга сводятся, да. Вот именно те работы, которые я имею в виду, там именно для капута и разные краевые задачи, в том числе и каши, и явные представления получает.
А здесь можно посмотреть краевую задачу на отрезке 0,1, скажем, по t?
Вот как раз вот это Луиза Гацева как раз такие задачи рассматривает там для 1.
И лямбда тогда можно изучить спектр.
Да, да.
И он не похож на обычный спектр Штудема-Белвилля, нет?
Ну, насколько я знаю, там есть какие-то результаты у нее, связанные с тем, что конечность вещественной части спектра, что вещественных собственных значений может быть лишь конечное число. Вот такого типа результаты есть.
Потому что вот это при рассеянии космических, ну, диффузий, вообще это не диффузия космического излучения, там субдиффузия. Ну, смотря как, если там правый оператор тоже дробный, то это уже супердиффузия будет. И там спектр очень важен, что вы... Ну, понятно, значит, здесь можно такие задачи посмотреть. Так, есть еще какие-то замечания, вопросы? Салона Варма, any question? Some remarks, maybe? Нет, да? По-моему, вообще-то все достаточно подробно было рассказано, понятно. Если нет, тогда позвольте поблагодарить докладчика и поблагодарить всех слушателей тоже. Варшава Жавович особо, потому что у него сейчас 12 часов, нет, что-то 3 или 4 часа ночи, да? Или 6 утра сейчас у вас?
Я уже 6 утра, Шавкат Ардаш.
6
Сейчас
утра,
вот 6:05, да.
Тогда можно сказать доброе утро вам, да, уже?
Да.